So just to announce a few things coming up, we have a busy several days ahead of us, last week of the program. So before I introduce this afternoon's speaker, I want to list that we have other events coming up. One is at 5:30 today, is sort of not quite part two of this talk, but a closely related talk by Henry Siegerman on that's right. Yeah, artistic mathematics. That's right. And tomorrow we have Jordan Ellenberg speaking at 3:15, and then we have the presentations of the Experimental Math Lab at 5:30, so for an hour and a half or so. And we have more activities later in the week, which I'll announce on Huva. Anyway, today I'm really pleased to sort of continue our, let's say, mathematics and artists in residence program. So we had our virtual reality workshop last week. And I just want to say we have a great long tradition of this. So first of all, Henry and Sabetta are longtime continued participants at PCMI. They've come for several years, and I'm pleased to have them back. But we've also had talks, talks on mathematical quilting by our own Irina Swanson in the past. And we've even had a talk about category theory and square dancing. It's a real thing. So anyway, in continuing on with this theme, I'm really pleased to have Sabetta Matsumoto. She's a professor of physics at Georgia Tech, and she's famous for her study of knitted fabrics and their mathematical and mechanical properties. She's been profiled in the New York Times and is, really a great expert and a really interesting avenue of thinking about the interaction of math and the outside world. So anyway, we're very pleased to have Sabetta, who will talk about twisted topological tangles.
Hello, everyone. How's everyone doing today? Everyone have a good weekend? Awesome. Yeah, we just got here over the weekend, and it's been absolutely gorgeous. It's been great to be outside and getting some fresh air. So does anyone here knit or crochet? Okay, I see a few hands here. So for those of you who don't, maybe you'll think about maybe taking up a new hobby after this talk. So I am, I guess, a lifelong knitter, and basically what I've done for my career is take every hobby I ever had and then turned it into work, which maybe is a good idea and maybe isn't a good idea, but I basically have been spending a lot of time thinking about knitting as both like a way of thinking about math, and also, because I'm in a physics department, kind of connecting the math and topology to the mechanics of what's going on. So I will tell you a little bit about the sort of journey through that, and if I have time at the end, I will get to sort of some unpublished work that has some pretty, so as a little bit of relationship to statistics and things like that, because I guess you all have links to things like probability, so maybe that'll be a topic that is interesting to you. So before I get, let's see, okay, before I get into the meat of the talk, I really wanted to thank all of the people who have been working with me over the years to try to accomplish a lot of these goals. So primarily, I would like to thank Shashank Markande, who is here, who has worked a lot on the sort of connecting the topology of stitches to mathematics. So he's sort of worked on ideas of things like what can be knittable and thinking a lot about knot theory and that point of view. I'd also like to thank Mike Dmitriev and Sarah Gonzalez, who have been the primary sort of computational folks on my team. So they've been dealing a lot with trying to simulate yarn and things like that. And Krishna Singhal and Alex Kashin are the primary experimentalists who, we have a huge industrial knitting machine, and so they have run that and fabricated tons of samples that we can then go test. Okay, there we go. So I guess I will talk a little bit about why knitting from two levels. So one is the level of maybe socially and globally why we should care about textiles and things like that, and then maybe why we should care a little bit from a kind of like intellectual historical point of view. So to start out with, textiles and particularly things like fast fashion have had a absolutely enormous impact on our environment, and have had a lot of social consequences as far as things like the rise of like TikTok fashion and Instagram, places where garments are not meant to be worn, they're meant to be photographed. And so the problem with this is this causes huge amounts of waste. So we generate over 95 million tons of post-consumer waste a year. So this is just in clothing that we throw away. A lot of this is also in clothing we donate. When we donate stuff that's not good enough to sell, then the places we donate to are responsible for throwing this away. And this either goes into landfills or gets shipped off to other countries where it sort of becomes these huge textile landfills. It consumes 79 trillion liters of water a year, produces over 1 billion tons of CO2 per year, and maybe one of the interesting things that maybe we're not used to thinking about is the microplastics waste. So it can generate 200,000 to 500,000 tons of microplastic waste a year. And this happens primarily when we wash our clothes. So when you put them in the washing machine, you have water and soap, and this agitates them around, and tiny fibers from our fabric get washed into the water system, and the filters are not able to filter these out, whether this is at municipal waste things. I know they sell filters that claim to do this in your own washing machine. They don't get down to the submicron or the micron sort of scale that these are. So it is really difficult to recycle textiles. And this is due to they have a very complicated hierarchical structure. So in a single fiber, or a single thread that would make up, like here, I'm actually not wearing a ton of stuff that's knitted today, but I have my overalls are woven. I guess my shoes are knitted. If any of those fibers are made up of these tiny little staple fibers that are then twisted into ropes, and then those ropes are coiled around each other, and you get one fiber like this. Then you take these, and then you would knit it into a structure like this. So this is a monofilament, so you can see just what the knitting structure is. But in a actual textile, this would be inside of all of these fibers here. And so one of the things is that when you have fibers in this configuration, it's really easy for you to introduce lots and lots of different types of material. So you might think, oh, knits are made out of wool. So that's one thing you can put in. You can also have cotton blended in, but the textiles industry says, well, those are very expensive. So we're going to use things like polyester, which is really cheap, but it is derived from petroleum-based polymers, which means that recycling that is not so easy. And the problem is when all of those are blended together into this hierarchical structure, you can't mechanically separate, oh, the cotton goes here and this can be reused in cotton things, and the wool goes here and it can be, put with other wool things, and the plastics go here and they can be melted down and put into a water bottle or something like that. That process just cannot happen. So we're kind of interested in taking the mechanical properties and the sort of advantage you would gain from having things like polyesters, or another thing that they put in a lot of fabrics is elastane, which is the chemical name for things like spandex and lycra. And so what that does is that gives it a sort of an artificial amount of stretchiness. So we're kind of interested in being able to modulate the topology of the stitches, which you can do on the machines that all of our clothes are made on, and then take those materials with more responsible fibers and put those into practice. So I guess the other way of thinking about this is thinking about knitting from sort of a historical point of view. So our group, we do like to think about knitting as a type of sort of mechanical computation. And you can look at this at like many different levels of sort of abstraction, if you would like. So at a very basic level, normally we think of coding as sort of, or code as like binary strings or something like that. So we have strings that the machine reads and outputs a final response. So we do the same thing in knitting or crochet or weaving, where each of these little symbols, I guess this is a grid, each of the little symbols in the grid is coding a different topological move for the stitch that would occupy that space. And so each of those stitches can encode things like mechanical properties. And then when you pull on your material, then those mechanical properties interact in nonlinear ways, and you can use that to get sort of a mechanical processing, if you will. And this isn't a very new analogy. This is something that has existed for, I guess, over 200 years. So in the early 1800s, this is a jacquard loom, and this is the world's first binary technology. And so what happens in weaving is that you have a rectangular grid of positions, and you can, at each position, you can decide, does the yarn go over or does the yarn go under? And typical looms sort of have a few different possibilities you can have, and then you can sort of use combinatorics to make several types of complicated fabrics. But the thing about the jacquard loom is it made every site on that grid individually addressable. So with the individually addressable nodes, you can program any pattern you want, basically. I can't guarantee it'll be a great textile. Like, if this one here is over and everything else is under, the whole thing will fall apart. But it still is a way of taking code and inputting it into a textile. And these were done using punch cards. And all of the technology that was used in this jacquard loom was then later used in terms of the mechanical computing that came along with people like Charles Babbage and Ada Lovelace. And these machines are still used. So here is an example of a textile that is being woven, and this has, I guess, 3 different portraits of a person on them. So you can get them to be basically as complicated as you want now. They're sort of very low resolution photograph reproducers at this point. So we do have very similar technologies to this with knitting, but one thing that I guess I mentioned before that I think is quite interesting is the connection to mechanics. So what every little pixel you have here has a different topology, and then that corresponds to a different mechanical property. And one question that you might think to ask as a mathematician is, what can I put in here? Like, obviously there are probably a dozen different symbols, if not more, on this one pattern piece. But are those the only things you can have? Did they leave things out? Are there things that people haven't done before? So that might be a question that you'd want to ask as a mathematician. So before we get to that, let's think a little bit more closely at what knitting is. And so a lot of people do think about knitting from a machine point of view, I grew up as a hand knitter, so I kind of like thinking about how it would work when I manipulate my hands with yarn in it. Our lab, we do have an industrial machine, so we can, not waste everyone's time by spending hours manufacturing little teeny rectangles. We can just ask the machine to do it, and it takes like, I don't know, 2 minutes. But basically the idea of knitting is pulling loops through loops. So what I have here is 2 knitting needles, so one in my left hand and one in my right hand. And in my left hand, I have a series of loops on the needles. In my right hand, I have a series of loops on my needles, but I also have the last loop is connected to this piece of yarn here. And I'm gonna call this my working yarn. And what happens when I take a stitch is I put my right needle into the first loop on my left needle, and then I take my working yarn and I wrap it around my right needle, and I pull it through the loop on my left needle, and then I can slide the yarn off my left needle, and I end up back here in picture 1 again. So basically, this is just a process of pulling loops through loops. So on one hand, you might think, okay, well, that's trivial. If I just remove those needles and pull on it, the whole thing unravels. So there's no topology here. But typically when we make these, we do kind of use the needles or sort of like what's called like a bind off as a way of sort of securing all of the stitches as if they were still on the needles, and that keeps them topologically secure. When we look at each stitch, we can kind of look at textiles. Like the textile I made before is this textile. That's what was shown in the slide, the previous slide. And we can look at an individual stitch. And so this individual stitch, because this is a periodic material, we can think of this as living in a torus that has been thickened. So I can't just live in a torus because I need to have information about over and under crossing. So we're going to carry a little bit more information than just a regular torus. But from here, you can see that basically I take one loop here, and that has been pulled through the loop on the row below. And if I look at it from the top of the fabric here, I have these sort of V-shaped structures. And that's typically what people would call the front of the fabric. This fabric is called stockinette, typically, where stockinette comes from the word for stockings. And if I turn it over and look at the back of it, here I will have pulled the yarn from the front of the fabric through to the back. And instead of a V, I have these little dashed ridges that sort of alternate. So not quite like an equal sign, like a shifted equal sign. And so that's what this side of the fabric looks like. And this is the most common fabric that is knitted. In machine knitting, we would call it jersey. And this is what basically everything is made out of. So this is what t-shirts are made out of. It's what socks are made out of. It's what sweaters and hoodies and things like that are made out of. So I can basically guarantee that everyone, because no one here is walking around naked, is wearing some of this material right now. And that is just how common it is. And we don't really know a lot about it just because we don't think about things that affect us every day. So I have a little piece of that here. So it's this navy blue sample. And this does not lie flat. I guess I can show it to the camera over here too. This doesn't lie flat in the plane. It wants to sort of curl up. And you can see that right here. And this is a pretty robust fabric. It's pretty stretchy if you pull on it both horizontally and vertically, but it's got like, it's kind of stiff. It's got some like give to it. So you can feel that. So I can combine these two stitches, these knit stitches and purl stitches, in different ways to give me a totally different set of mechanical properties. So just by changing the topology, I have a huge amount of tunability of my mechanical response. So if you look at this first one, I have alternating rows of knits and purls. And this is fabric called garter fabric, and this is garter as in garter belts. So these things are named after what they're typically used for, or were typically used for. And this is the orange sample here. This one doesn't come out of the plane. It is very flat, and that's because it has the same number of purls as it does knits on a fairly small scale level. And this one, it's pretty stretchy horizontally, but it is very stretchy vertically. I guess one way to keep this straight for all of them is there's two strings that hang off of the side, and one should be on the bottom, one should be on the top, and that should help you orient the fabric. The next one we have is 1x1 ribbing. So this is alternating columns of knits and purls. And this is another one that's very commonly used in industrial textiles. This is, I guess, this olive green one that I'll pass around. And it's used in cuffs and collars. So this one is about as stretchy as the first one in the vertical direction, but in the horizontal direction, it's about an order of magnitude stretchier. So I have about like a 10x, 12x variation that I can tune by playing around with these different combinations. And so this is used in cuffs and collars, so places you'd want them to expand a lot to fit over your head or around a wrist or something like that, and then sort of shrink back to their original size. And then the last one I have is a checkerboard lattice of knits and purls, and this one is the bright pink one. And this one is the most sort of isotropic of all of them. So pulling it in the horizontal and pulling it in the vertical directions are by far the most similar to one another. So you can feel that. So if we wanted to look at this from a point of view of knot theory, we can look at knots in the thickened torus. So the notation for this is T2 cross I, where I is the interval. So I'm just taking a regular torus and thickening it up. So here I'm going to sort of show you what this might look like. So I would like to take the left and right sides and join them together, and also the top and the bottom sides and join them together. So I'm going to do that right here. Well, hopefully I'm going to do that right here. There we go. Okay, so first I'm going to sort of extend the left and the right side so you can see that I'm wrapping the top and the bottom sides around behind the knit. And then I wrap the left and the right sides around behind that. And then this structure here looks like a trefoil knot here and a trefoil knot here. But there's a little bit more structure to it because I have to keep in mind what my tori looked like. So here I'm going to draw in the tori at the front face, so that's in yellow, and then the back face, which is the torus in green. So this structure, along with the two tori, are enough for me to define the topology of any of my stitches as if they're knit. And so I guess I like to think about textile knots then as living in the glaze that's on the surface of a donut. So that's, I guess, a little bit sticky, but that's sort of a nice way to think about the space that all textile knots live in. So if we wanted to look at this structure, oops. So I guess if we want to look at the structure a little bit more closely, what I'm going to do instead of drawing in the whole torus is I'm going to sort of encode the topological information about a torus by having two linked cycles. So one will go through the center of the yellow and loop around like this. And I think I have that as green in my next slide. And then one will go through the center of the green torus, and I think that'll be red on my next slide. Oops. Okay, so here I start out with the little chunk of knit as we've seen it before. And I'm going to put it into the thickened torus, which is really the ambient, I guess S3 is the nice way of looking at it for knots, but you can think of it as R3 with the information encoding my torus. And so when I do that, I can put it in here like this. So you can see the green one is through the center of the yellow torus, and the red one is through the center of the green torus from the prior page. And now I'm going to glue the left side to the right side. And I wrap it around and I glue it like this. Now, if I want to glue it to the top side to the bottom side, I need to keep in mind that I need to wrap everything all the way around the red cycle. So I'm going to do that. I'll try to, I don't have a great animation, but I will sort of pull up the top and bottom to sort of show you that I'm pulling it backwards, and then wrap it, whoa. Okay, you're a very excited presentation. Okay, so, or maybe I'm just talking way too slowly and that's where I should be. So here I have two annuli, a green one and a red one, and those meet along a single line here. And I have these curves, this green curve and this red curve, and they're sort of keeping track of my thickened torus. So I can rearrange what this looks like. And basically what I have is the knit stitch that I care about and then some gadget around that keeps track of the topology in the thickened torus. So I can ask questions like, what should go inside this piece of my structure? And that is the question that Shashank Markande was working on for his PhD. So we started this by, first he learned to knit. That's not a typical prerequisite for becoming a physicist. So, so first he learned to knit, and then we had all of these stitch dictionaries. So there are all these books that have sort of historical stitches and things like that in them, things that people use, patterns, whatever. And then he was sort of looking at them from a knot theory point of view, trying to think a little bit about like, are there any sort of properties, invariants, things like that that are common between all of these, so he could start forming a conjecture about them. And he noticed that all of the stitches have a property that they're called ribbon. And I'm just going to give you a very cursory definition of it because the real one involves some dealing with stuff in 4 dimensions, so we can skip that for the point of view of this talk. But basically, the idea of a knot that is ribbon is, imagine you have your knot and you use that as a boundary of a disk in R3. Then the disk can interact with itself in a number of different ways. But ribbon restricts how the disk can interact with itself. So in a ribbon knot, the disk can only pass completely through another portion of the disk as if it is a ribbon. So you cannot have things that look a little bit like X's. And so that basically means that when I'm doing my knitting, because you can think about it as how I've like pulled loops through loops. So I'm sort of taking the loop, and then any manipulation I have is kind of on that doubled piece of yarn in my loop. And so you can kind of think of it intuitively that way as to why this might be a property that you would see. And so Shashank was thinking about this, and we were also sort of thinking about the converse of it. So is it the case that all ribbon knots are then knittable? And so when he was thinking about this, he was thinking about like what are ribbon knots and what may or may not be knittable. So so he sends me a text with this picture in it. And so this is ribbon, but then the question is like, is it possible that this is knittable? And so so I was like, well, I don't know. Why don't, like, let's bring some needles and yarn on Monday, and we'll sit down and figure it out. And so I did, and this is the result of that. It is in fact knittable, and so Shashank called this the cow hitch stitch. So this is like similar to a cow hitch knot, and this is like really incredible. So Shashank, who had come to school to study physics, ended up doing something between math and textiles, has now discovered a new knit stitch that no one else had ever done in the history of knitting, which I think is really incredible. And he did it because he understood the math behind what was going on. And you might ask, well, can I make fabrics and stuff out of this? And the answer is yes. So this is a fabric where I have these stitches alternating in a checkerboard lattice. So I will say that I don't notice a huge mechanical difference between the stitch and a regular, just a regular knit stitch as far as the overall textile. It does, I think, maybe make the textile a little bit more like effectively porous because it kind of holds the stitch together a little bit better. But it does make a nice little kind of decoration. Like you see these sort of little dollops everywhere. So I think that's quite nice. And just to let you know, for the two conjectures, the conjecture that everything is knittable is ribbon is true, so we do have a proof of that. We also have an incredibly long definition of what knittable means. So I guess the answer is yes, but the answer is no, I'm not going to show it to you because that would take like 20 minutes. The converse, are all ribbon knots knittable? The answer to that is no, unfortunately. There are ribbon knots that we can't knit based on our definition of knittable. You can show that there are, what's the word? Well, it doesn't fit into the definition. All right, so I will talk a little bit about the mechanics side of this. I'll try to go maybe a little bit quickly through the first bit of this so I can get onto the bit where we look at kind of statistical properties of our knits. This is just kind of formalizing the intuitive information I said before when I was passing around the samples. So basically, this is our industrial knitting machine. And here it is basically knitting, this is knitting a scarf. Normally, if we were knitting one of our swatches, you would not be able to see much because it's all just trapped inside the machine here, which is not interesting, but here's a scarf being made. And then we take those and we put them in into a machine called a UTM, which is a universal testing machine. And we can basically do mechanical experiments. So this measures the force that is being exerted as well as the displacement. And you might be saying, like, Sabetta, you should take better care of your samples. This one is completely gross. And it is gross on purpose. So what is going on is we've coated it in speckles made out of, what's it called, graphite powder. And so this is because we're putting it through a computer program that does something called DIC, which stands for digital image correlation. And that's basically looks at an image and says like, this part of your image is the same as what this part was a few frames before. But it's computer graphics, so it's not very smart. So it thinks that every stitch in a fabric looks exactly the same, and then tries to map them all to the same place so it breaks. But if we make the texture look kind of gross enough, it can't tell what's a stitch versus what's like a blob of graphite, and that enables the software to have a random enough set of patterns that it can measure this. And I'll show you some results of what we get from that type of measurement in a little while. So, oh, wait, I have it right now. I thought I had this a little later. So basically, this is what the result of digital image correlation on these like very simple samples are. So here I'm tracking the displacement in the x direction, and here I'm tracking the displacement in the y direction. And once I know those displacements, I can take discrete derivatives on them and figure out both how much a particular bit moved, but also how much it moved relative to all of its neighbors. And if I know how much it moved relative to all of its neighbors, I can basically do a mini version of Hooke's law, or maybe a more complicated version of Hooke's law, on all of those little nodes and figure out the mechanics that are going on inside. So we also ran these through a computer, and we basically did this by taking our original sample and breaking our yarn up into different regions. So we have regions where the yarn is interacting with other yarn, so it can sort of feel a compressive force from a different piece of yarn, and then yarn that's joining those together. So the only force that that yarn is feeling is bending. And so we can assemble this into a little graph and start trying to understand what's going on. And so our yarn model puts these in periodic boundary conditions, and then it fixes the total length of the yarn. We can put some energy on it, which we basically say that the energy comes from bending and twisting, but the twisting, in our case, the constant J is so small that we throw it out. And then we have to look at how pieces of yarn interact with each other. So basically we have a model that when the cores of the yarn are farther apart than 2 yarn radii, they don't interact. And then as they overlap, they have a power law interaction with a cutoff where it's sort of infinite beyond some radius. And then we can run basically the same experiment we ran in the that I showed with the actual fabric in our computer and look at some different results. So this is a plot of basically we're looking at force in the x direction here, so force horizontally here versus displacement in this direction. But these are normalized so that the absolute quantities don't matter. We would call this in engineering a stress versus strain curve, but you can think of it as sort of force versus extension. So that means that this rib fabric, if I pull on it, I can extend it quite a lot for a very small force. So if I extend it to, I guess I've extended it 50%, or actually, sorry, 100%, it will be at, I guess, a force of like 0.025 in whatever units. And if I compare everything else, I will have only extended it by something like, I don't know, 15%. So you can see that that would make this rib fabric way more extendable. And if you look at the slopes of these that tells you approximately the stretchiness. So that's like, if you're thinking about a Hooke's law, you've got, I guess, force equals minus kx. The slope here is the k. So a stiffer slope means it's harder to extend. And so we can basically look through these and sort of look at why these might be. And so we basically looked at the topology and sort of symmetry of these to see where this might come from, like why they might be so much stretchier than the others. And so here I'm looking kind of down, like from the bottom of the fabric, like horizontally through the middle of it. And so I have in the light blue, this is a knit stitch, and this is a knit stitch, and this is a knit stitch here. And then I have like these pieces of yarn connecting my knit stitches. And because every knit stitch is the same as every other knit stitch, this connecting piece of yarn has to have even symmetry. So if I'm looking at it, I have like an under would be the sort of symmetry of the crossings. And so I can do a little calculation that says, okay, I have the distance across here is lambda naught, and the total length of my yarn is L. I'm gonna stretch it a little bit to go to lambda, or lambda naught plus delta lambda. I'm gonna keep the length being L, I'll keep the normal vector being the same, and then I can find that my K is 180 times some units. The units right now don't matter, just the 180. If I looked at something where I have a knit stitch next to a purl stitch, here I don't have the same symmetry in my connection. I have now an overcrossing next to an undercrossing, so this connecting piece of yarn has odd symmetry. In addition to the other two pieces of information, we've got an angle that the vector that connects the starting point and the ending point of that yarn segment makes with the horizontal, so that's phi. I can do the same experiments, and I find that the constant k is now 12 times the same coefficients times 1 plus a correction factor. And basically, that means that the even crossing topology has about 15 times stiffer mechanics than the over-under crossing topology. And so basically, we can look at what this means, both looking straight from the sort of bottom up and from the side up, and calculate what these look like. And so I'm showing here that like k value effectively here, it's called y, between the experimental samples we're showing here and then the model that I just calculated for you with all of the constants appropriately plugged in over here. And so all of these basically lie along the x equals y line. So that means that our prediction is pretty accurate just by taking into account topology and a couple of different yarn parameters. We can predict the behavior of different fabrics. And we can do the same thing with different types of fabric. So here I have things that are made out of bamboo. There's, I think, mohair, wool, all sorts of things, and of different thicknesses too. So we can say that that this is not exactly the same measure. This is comparing the x direction behavior to the y direction behavior, so we don't expect it all to lie along the x equals y line, but we're showing that the different types of stitches are grouped according to the ellipses here, so we can see that they have like fairly tight behavior within their own topological categories. what we were able to do is to show that instead of sort of manipulating the different types of yarn we would use in a device, we can manipulate instead the stitches. So here I have a glove, which I'm not going to pass it around, but you can come up and play with it at the end if you're interested. So the glove I have, it's all the same yarn, it's just dyed different colors. And this piece is knitted as one piece and then sewn together along the thumb right here. And so we can see that the different pattern types were chosen based on how a hand might want to move. So here it's designed to provide like wrist support, so it's quite tight along the wrist and kind of has a little like thumb hole to help keep all of that aligned. Not a doctor, not medical advice, just an example. And the different types of other materials are designed to match structurability. So the orange piece up here, this is garter, so that's designed to allow my fingers to move like this. The back of the hand has the green one on it, that's ribbing, so that lets my fingers bend like this. The pink one here is for the thumb, and because the thumb can move in all directions, we wanted to use the most isotropic material. So basically, we're kind of arguing that instead of maybe making this out of lots of different blends of material, you could make the same thing out of one type of material, just changing the topology to enhance functionality. Okay, so we were also interested if we were to look at a grid of these. We're physicists, so to us this looks a little bit like an Ising model. So if you have a knit is like a spin up and a purl is a spin down, what happens when we look at different random knitted fabrics? So first we can look at what happens if we were to say have a 50-50 probability of each element having a knit versus purl stitch. And what I'm showing is that in green, these are boundaries where you have one stitch next to a stitch of a similar type. And then the white boundaries are where you have a stitch of one type that's next to a stitch of another type. So in our analogy before, these white lines should be soft, but the green lines should be stiff. And so that makes us think, well, what if we change the scale of the randomness? And so we can look at this. So here, this is another thing that's random, but I guess you can imagine a subsampling it. And so here we have different domains appearing. So this is a domain that has percolated. And so would this, having percolated, have a different set of mechanical properties than the prior slide? And so we looked at this. We're going to run something called Cahn-Hilliard dynamics, and this is a model for two-phase separation. We don't necessarily need this model. We can do anything we want. It's just that this model has really nicely characterized statistics. In particular, everything about the domain size and shape is self-similar under a specific scaling of time and dimension. So what we're going to do is we're basically going to seed a Cahn-Hilliard model with something totally random and let it run for a long time and take snapshots of it at different times. Let's see, how am I doing on time? So we can look at different types of phase separation here. We can look at where we separate, the phase separation happens along a horizontal line. So here we have percolation in the horizontal direction, but not the vertical direction. And so we could look at the behavior of this progression of our statistical model. And this is what the fabrics look like. So you start out with something kind of lumpy, and then the lumps get sort of larger and larger. And then once it seems like it has maybe percolated, you start getting a lump here that starts sort of rolling up, and you get this sort of spiral. So here, basically, there's sort of a spiral between the top half and the bottom half. And so we would think that this is very, very, very soft, because you now just sort of have like, not quite an accordion, but sort of a spiral that like can sort of untwist to unfold. And so we can, if we were to look at the those force extension curves, we can see that they get sort of softer and softer and softer with time step. If I looked at the opposite separation, so this is what the this sort of curlicue spiral looks like, and why it's so easy to unfold. So that's why we have such a soft behavior. And we can plot here we call it a Young's modulus, but it's that effective like K stiffness, and you can see this is on a log-log plot that it starts out, it gets a little bit softer. In this middle area, it gets way softer. Sort of after, sort of in this sort of about where we're getting large-scale percolation, it sort of reaches pretty close to its softest, and then it sort of stays about the same softness as long as it can roll up those spirals. In vertical phase separation, we get something similar, except that here the percolation happens vertically. And this is what the fabrics look like. Again, you cannot distinguish the first few of them. These ones look similar-ish, but then around here you start to notice that the behavior is totally different. So here you might get a little bit of a spiral, but it is separating two things that are sort of one vertical strip next to another vertical strip. So if I were to pull on this, I don't get the benefit of that extra spring. And you can sort of see this in this plot. It's not so easy, but if I looked at like red, orange, yellow, green, green, blue, blue, purple, we don't see that this is sort of a monotonic order of all of the plots. And so what we show instead is that we start out with something that is pretty random. We sort of let it evolve. I guess this one gets slightly stiffer, but it stays about the same. Then it softens up a lot. Then after we get this sort of vertical percolation, we start to get significantly stiffer slope. So this is almost as if there's a phase transition here. We have fabric that wants to behave softer, 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 and then when we get I should also mention that I'm using percolation in a slightly different way than normally you think. I'm thinking of percolation as in a single row is connected top to bottom with one color, not just system spanning. Sorry, I forgot to mention that earlier. So this one, there's no straight line that I can connect from the bottom to the top that has all either black or white lines, but here I can. Sorry, I forgot about that. So basically we can look at sort of classifying these into sort of similar behavior types. So when the disorder has is small compared to the system size, we get kind of, and maybe it goes up, maybe it goes down, but it stays pretty similar. Then as it starts to sort of coarsen a lot, it softens a lot. And then at the point of this directional percolation, I'll say, it splits into either very soft or very stiff behavior. And I think this is just illustrating that whole system again, looking at the particular patterns of it. And this is what we've done when we have 7 different initial seeds for each one in both directions. So this is sort of a full set of data. So we're trying to do statistics on the statistical model and not just on one sample. And this is maybe the exciting version of the DIC, but this is sort of showing how the different regions within the sample extend more or less. So the red is a lot of extension and the blue is very little extension. So you can sort of see how it's not evenly spread across the fabric as it was at the very beginning of the talk, but here it is much more localized to areas where you have these regions that are knit next to pearl. And so I guess the moral of the story is that we want to look at different ways of making better materials by looking at their microstructure, in particular their topology. And we're sort of interested in ways in which we can use mathematical ideas to engineer things for the real world. And with that, thank you.
Thanks very much, Sabetta. So are there any questions? Paul.
Do you know what the probability that ribbon knot will be knittable is? In other words, is it rare that a ribbon knot is, are there very few knittable knots among ribbon knots?
That's an interesting question. You know, we haven't looked at statistics from that point of view. We've sort of tended to look more at sort of, single examples and then trying to like generalize some properties rather than kind of looking at families and sort of, it wasn't that easy to actually well, no, it's pretty easy. Like if you look up ribbon knot on Wikipedia, I think one of them is not knittable. But it's just the proof of showing it's not knittable is not so easy. So I don't know, you know, it feels like it's going towards one of those like slice knot problems where I need to understand a lot about the Morse function that I don't know about. We can do it constructively, but not necessarily from the other point of view. So, but very interesting question. Oh, sorry, go on.
Just a follow-up, completely different question. Have you thought of going into business, selling?
I would be the worst business person in the world. I don't like answering emails. I would say the point of making money does not bring me joy.
Do those gloves feel good?
No, they actually feel terrible. So basically, so compression stockings are measured in milligrams of mercury. So it's usually like 20, 30, 40 milligrams of mercury. So I was like, okay, we should make this like compression stocking level. So I think it is like 20 milligrams of mercury, which feels terrible on your wrist. That is not, I mean, not doctor, don't take medical advice from me. But I mean, I'm sure if we had someone who knew something about wrist physiology and, you know, actually the directions you want to put compression on, that's fine. But, you know, assuming that, oh yes, wrist is the same as like my whole lower leg, that was a problem.
What could go wrong? Any other questions? Yeah.
I guess one of the things that makes knitted fabrics easy to waste is that the moment you snap one thread, you get a pretty big vertical hole. Do you guys have any ways around that?
So that's called laddering because like after it splits up, it looks like there's a little ladder left. So we haven't ourselves looked at that failure. I think I saw someone who was doing her PhD give a couple of talks on that and like how pulling it causes it to propagate in different directions, like under different amounts of tension. So there is that. I also did meet someone who was maybe doing I'm forgetting if he just finished his PhD or is just starting his PhD, but I think he's just finishing his PhD, but is maybe going to start a postdoc who was doing computation like trying to do like actual computation models on knits who has a method to get around laddering. But I don't think you can put it into an industrial knitting machine. I think that's something you can only do with your like hand knitting.
The original diagram grid you had, you said 12 symbols or something, but here you use only knits and purls. What if you add some of the other stitches? Would that change your...
Absolutely, that would change a lot. My very simple model said that every stitch is the same as every other stitch, but they're connected by different types of springs, basically. So what that would say is that every stitch is not identical. So I can have I could have a very stiff spring or a very soft spring as my like stitch itself. And then again, those would still be mediated by similar types of connections, whether they're stiff or soft. But I think that would make, so we have very like granular differences. Like I'm like, okay, here is one type of fabric and here is a type of fabric that is like 10 times softer. But getting like different places on that gradient is not necessarily easy. So that would help us like target very precise values that we're not able to get right now.
Okay, anything else? Okay, let's thank Sabetta again very much.